Hello everyone, we are from Group 6 and today we will presenting our group assignment from the subject Statistic and Spatial Analysis. So, the title of our project is Multiple Linear Regression Analysis, the Impact of Climate and Land Cover Factor, Groundwater Recharge Rate. In this study, we use SPSS software to analyze how the independent variable, regression cover, average monthly rainfall, and temperature influence the groundwater recharge rate, which is our dependent variable. First, we will show you how to obtain and enter the data into SPSS. This includes setting the variables, entering the data sets, and running the multiple linear regression analysis. After that, we will proceed to answer each question based on the SPSS output. So now, let's take a look at how we get the data into SPSS.
Multiple linear regression is one of the statistical methods used to help us analyze how several factors, which we call independent variables, can collectively influence a single outcome, known as the dependent variable. This means we are looking at how a group of inputs works together to affect a single output. Specifically, this method can help us measure the extent to which each of these factors can contribute to each change in the outcome. So, it tells us not just that they have an influence, but also the degree of that influence for each factor. Next, based on the given case study, the dependent variables is the groundwater recharge rate, measured in millimeters per year. This variable acts as the most important output that is to be predicted based on changes in several other variables. It's the central outcome we're trying to understand and forecast. Meanwhile, the independent variables include three key factors, which is vegetation cover, measured in hectares, average monthly rainfall, measured in millimeters, and average temperature, measured in degrees Celsius. These independent variables play a vital role as predictors in the multiple linear regression model. They are the factors we believe influence the groundwater recharge rate. We use them in our model to analyze the relative effects of climate factors and land use management on the rate of groundwater recharge. In essence, these are our explanatory variables that help us predict the changes in the groundwater recharge rate.
After conducting multiple regression analysis, we were able to formulate the relationship between the rate of groundwater recharge. Based on the coefficient obtained from the output of statistical software SPSS, our regression equation is as follows: 0.419 for constant, 0.016 for vegetation cover, 0.003 for average monthly rainfall, and negative 0.016 for average temperature. To get the groundwater recharge rate, 0.419 plus 0.016 for vegetation cover plus 0.003 for average monthly rainfall plus negative 0.016 for average temperature. This equation becomes our model to illustrate how the independent variable, namely vegetation cover, rainfall, temperature affect the dependent variable, namely the rate of groundwater recharge.
So for the question 4, here we can see that the R square value is 0.971 and the adjusted R square is 0.966. This means that 97.1% of the variation in groundwater recharge can be explained by the three independent variables, which are vegetation cover, average monthly rainfall, and temperature. Only 2.9% of the variation is not explained by the model, since the R square value is very close to 1. This tells us that our regression model is very strong and highly reliable. Therefore, this model is effective in explaining and predicting groundwater recharge rates, particularly when we consider climatic and vegetation cover factors.
Okay, now we move to the question 5. Conduct a global hypothesis to determine whether the model is significant. 4 marks. Now I will show you steps to answer the question. First, state the hypothesis. We need to state the null hypothesis, null hypothesis and H1. At least for the null hypothesis, all regression coefficient are equal to 0, and for the H1, at least one coefficient is not equal to 0. Now we will use the ANOVA table from the SPSS output. For the F statistic, we determine that 179.052, and for degree of freedom of regression we got 3, and residual degree of freedom we got 16. For the p-value significant we got less than 0.001. 3. Decision rule. At the step 3, decision rule. At alpha 0.05 compared to the p-value to alpha. Since p less than 0.001 less than 0.05, we reject the null hypothesis. The final answer to answer the question based on ANOVA table, the F statistic is 179.052 with a p-value less than 0.001. At the significant level of alpha equals 0.05, we reject the null hypothesis. Therefore, the global hypothesis test indicate that the regression model is statistically significant, meaning that at least one of the predictor variable contribute to explain the variation in the groundwater recharge rate.
This regression model involves three main independent variables, namely average temperature, vegetation cover, and average monthly rainfall, which are used to predict groundwater recharge rate as the dependent variable. From the SPSS output provided, the R square value obtained is 0.1971, while the adjusted R square is 0.966. This indicates that 97.1% of the variation in groundwater recharge rate can be explained by these three independent variables. The adjusted R square being very close to the R square suggests that the model does not suffer from overfitting and remains stable even after accounting for the number of predictor used. This demonstrates that the model is statistically very strong. To determine whether any of the independent variables in the model can be removed, individual hypothesis testing must be conducted. This is usually done by referring to the coefficient table in the SPSS output, which contain the p-value and t-statistic for each independent variable. The null hypothesis states that the regression coefficient of a given variable is 0, meaning that variable has no significant effect on the dependent variable. If the p-value is less than the significant level, the null hypothesis is rejected and the variable is considered significant. However, the SPSS output does not include the coefficient table, and therefore the p-value and t-statistic cannot be obtained. Due to this lack of information, individual hypothesis testing cannot be fully conducted, and any decision to remove a variable cannot be statistically supported. Nevertheless, based on the high adjusted R square, we can reasonably assume that all three independent variables contribute significantly to the model. If any of the variables were weak or irrelevant, the adjusted R square would likely be lower. In conclusion, without the p-value and t-statistic, we cannot statistically confirm whether any independent variable can be dropped. However, given the strength of the overall model, none of the independent variables should be removed at this time.
Now, let's move on to question number 7. where we are required to predict the groundwater recharge rate using the multiple linear regression equation. The equation used is y hat b equal to b0 plus b1 x1 plus b2 x2 and plus b3 x3, where y hat is the predicted groundwater recharge rate in millimeter per year. B0 is the intercept, which is 0.419. B1 is the sufficient for vegetation cover, which is 0.016, and B2 is the sufficient for average monthly rainfall, which is 0.003. B3 is the sufficient for average temperature, which is 0.016. The given values are vegetation cover 142 ha, average monthly rainfall 415 mm, and average temperature is 24 degrees Celsius. Now, let's substitute the value into the equation. And finally, the predicted groundwater recharge rate is y hat equal to 3.55 mm per year. So, this value represents the expected recharge rate based on the given environmental condition.
So, in conclusion, our analysis shows that vegetation cover is the most significant factor influencing groundwater recharge rate. The model has a height R² value and is suitable for prediction and water resource planning.